We will carry on with the discussion on spectroscopy, the one we started last time. So, in the last class we looked at a very basic a set of very basic constants which are Einstein's coefficients A and B, where A resembles or A represents the spontaneous emission and B corresponds to the stimulated one, right. So, absorption can only be stimulated because only if you have light will, or if you have energy density coming in, will the molecule absorb and go up to the excited state. So, absorption has no counterpart or no similar counterpart as stimulated or spontaneous emission, right. So, there is nothing as spontaneous absorption. Absorption is always based on absorption of light. On the contrary, there are two ways that molecules can come down. One is stimulated, that means the light you are shining itself stimulates the transition from the upper state to the lower state, and the other one is spontaneous, that means you do not need any energy density, the molecule itself comes down, right. And then we went on to see that based on a certain derivation, taking equilibrium Boltzmann population into consideration, that there was a ratio A to 1 over B to 1, right, and we saw that this was proportional to nu cubed, and thus we said that the higher the frequency, that means the higher the energy, lower the wavelength, the higher is the probability of having spontaneous emission over stimulated emission. And that is why, because lasers are based on the principle of stimulated emission, it is so hard to get lasers which lays in the UV just because of this, right. This you cannot avoid. Okay. So, based on this, then we moved forward and started discussing another aspect which is very fundamental to spectroscopy, which is Franck Condon. Now, we are talking about electronic spectroscopy out here. So, this is what we said. So, if you are given, you see all these things were written in the last class. If you are given two electronic states, one is S0, which is the ground electronic state, right, singlet, the other one is S1, the excited singlet electronic state. Now, these are just examples, right. This is just there can be many other states out there too. So, but let us start with the very simplest one. Okay. Transition is always vertical in nature, right. This is what we are looking at, a vertical transition. This one, the crossed one, is a slanting transition. It should not be having any slope. The basic premise behind this being that electrons are much lighter than what your nuclei. So, when you are having a vertical transition, during the vertical transition your R is not changing, where R is what, the internuclear distance. That means, even before the nuclei can respond to that perturbation, your electrons have already moved to the higher state. That is why a transition is always vertical, that is why it is called a vertical transition. Okay. Now, this has many consequences, you will see as we go on discussing. But there is also a fundamental issue, but before going there, just to make the point, along with the electronic states which are S0 and S1, the borderline which are the electronic states, you also have these lines, right, these lines going across the electronic states. These are the vibrational states as shown out here. So, you will be having vibrational states for the ground electronic state, vibrational states for the excited electronic state, and whatever electronic state you consider, every electronic state would be associated with a set of vibration levels. And then obviously, the vibration levels will also be having rotation levels, right, all those things. But here we are mainly concerned about electronic and vibrational. Now, so you can understand one thing, that if I am going to do an electronic transition, that means if I am going to do a transition from S0 to S1, now just keep this thing in mind. If I am going to do a transition from S0 to S1, I am not only going to change my electronic excited state going from S0 to S1, but along with that I also have, depending upon how my nuclear geometry changes, I will show that to you later, I will also have a probability, a finite probability of populating vibration levels or higher vibration levels in your excited electronic state, right, because in the low electronic state you have V is equal to many, right. Can V be 0? The quantum number V, can it be 0? The quantum number V, can it be 0? It can be 0, right. So, the quantum V can be 0. So, you can have 0 to n for S0, you can have also 0 to n for S1, 0 to n for S2 and so on, because each electronic state is associated with a set of vibration energy levels. So, that is why I hope you have come across this word. There are certain group of transitions known as vibronic transitions. So, vibronic transitions, if you split the word, it would refer to vibrational, that is where the VIBR comes from, and ONIC comes from electronic. So, vibronic means a combined vibration and electronic transition. Okay. So, keep this in mind, we will come across this very soon. Now, the fundamental thing that I was talking about, okay, you are given a set of electronic states S0 and S1, and you are asked this question. The question you are asked is, what is the transition probability? What is the transition probability of this compound making a transition from S0 to S1? How would you figure that out, or on what quantum mechanical parameters should it depend? Okay. Now, this can be derived. What we will do is we will actually go through the derivation, and you will see how fundamental it is to spectroscopy, especially electronic spectroscopy, and what are the different components that come out, and why it is called a vibronic transition, not only an electronic transition. Okay. So, let us look at that. So, what you are going to do now is, we are again going to look at Franck Condon principle, and here we are going to introduce something known as transition moment. So, as you can understand, the transition moment, the transition comes from the transition from one state to the other state, right? And where does the moment come from? Where have we heard this moment before? The moment comes from the dipole moment, right? So, it must be, so there must be a combination of this transition along with a change in electron density or electron distribution. That is what would give rise to a change in your moment. So, that is why it is called a transition moment. Okay. Now, where do we start from? We again start from the Born-Oppenheimer's principle. So, what we say is your electron or your total combined wave function psi, okay, is given by psi electronic. So, the electronic is referred to as E r comma r times psi vibrational, this you can also write as psi nuclear, which is n depending on r, and this is equation 1. So, what is big R? Big R corresponds to what? The internuclear distance, that means the nuclear coordinates. R corresponds to what? The electron coordinates, right. So, big R corresponds to the nuclear coordinates, and small r corresponds to the electron coordinates. So, what you can realize is, if you split it up into two, the vibrational part depends only on what? The vibrational part depends only on what? The nuclear coordinates r, right, and this you know why, because when you are talking about a potential, you do half k x squared. What is x? X is essentially how much you are shifting from your equilibrium position r. Okay, x is essentially extension or compression, whichever you look at it. Okay. Now, the electronic, however, depends on two coordinates. One is the small r, which is the coordinates as defined by itself by its own position, and the other is defined by the nuclear coordinates too. Okay. It is obviously understood that when the electrons move, the nuclear would not be moving, they would be following, but still the nuclear would be moving. That means your transition is also accompanied by a vibration, right, that is what it means, and the moment you have a vibration, that means your nuclear coordinates are also changing, right. So, this type of dependence, that means psi electronic. So, sorry, let me write psi electronic r r, this is referred to as a parametric dependence on r. It is a parametric dependence on r. The parametric dependence on r again means that for each and every r, whatever r values are, which will help you give rise to a plot, you solve your electronic Schrodinger equation, and you get psi electronic, you get E electronic, and then you get the energy curve. Okay, this is referred to as parametric dependence. So, this is our starting point, right. Now, this is our starting point. So, what we have done is we have said that these two motions being independent, they can be decoupled from each other, but keeping in mind that the electron motion is still being governed not only by its own coordinates, but also by the nuclear coordinates. Okay. So, where do we go from here? See, it is like this. When you do quantum mechanics, there is one very important thing you always talk about, it is an operator. What does the operator do? What the operator does is, if you operate on a certain wave function with this operator, you will be able to do a certain action or a certain transformation, right. Okay. It is like matrix operations. So, similarly, if you would like to do a transition, you have to be able to operate on the molecule by an operator, the molecule being a quantum mechanical system by an operator, and only after you do this operation will it make a transition. So, then you can understand what is going to happen is, if you are going to find a probability which is related to this probability of transition, that means to what extent the transition would be taking place, you would be actually solving what? You would be actually solving what? You will be actually solving something which corresponds to an expectation value, where the expectation value involves two things, two major things. One is the ground electronic wave function, the other one is the excited electronic wave function, with an operator sandwiched between these two, because the operator makes this transition happen, as simple as that. That is why quantum mechanics expectation values are so important. So, if you are going for a position, what do? You take the position operator and sandwich in between the two wave functions, the same thing you do here. So, then our attention now shifts to what is my operator. Okay. To think about it, it is very simple. When you are doing a transition, what is essentially happening? You are shifting electrons from one place to the other place, from one orbital to the other orbital. Essentially what you are doing is, you are giving rise to a change in the charge distribution. Whenever you have a change in the charge distribution, this would be accompanied by a change in some sort of dipole moment, but this dipole moment is changing during a transition. Okay. Hence, it is referred to as a transition dipole moment or a transition moment. That is why it is called a transition moment or a transition dipole moment, as was written on the title of the previous sheet. Okay. So, then if it is the dipole moment we should be considered about, what we can write is the electric dipole moment operator can be written as mu, with the hat on top being the operator, is equal to minus E sigma I r I, the small r referring to the coordinates of the electrons, E being the charge, plus E sigma alpha z alpha r alpha. Okay. So, this is equation number 2. So, see, this can be further simplified as mu is equal to mu electronic, I always write here, sorry, mu electronic plus mu nuclear 3. So, that means your dipole moment has contributions from two things. One is because of the electron movement, and the other is because of the moment of the nuclei. Okay. So, if you would ever try to actually calculate something like this, you would introduce this dipole moment, electric dipole moment operator. Okay. Now, what do we do? Because this is the operator, this operator is the one which brings about the transition. We take this and we sandwich it between the two wave functions we are concerned. One wave function belongs to S0, say the ground state, and the other wave function belongs to the excited state, right, as simple as that. So, then what we define is, we define something, known as M. This M is referred to as the transition moment the m is referred to as the transition moment, and we get the transition moment by solving an integral. Okay, what is an integral? So, therefore, m is in your Dirac notation, m in your Dirac notation is given by psi mu psi. So, what is mu? Mu is the operator, right, which brings about this change. After doing the operation, you have this change from the ground state to the excited state. Okay. What are these two psis? One psi, say it is double prime, belongs to the ground state, and after you take the operator and operate on the ground state, where do you go? You go to the excited state, and that psi is referred to as psi prime. Okay, that psi is referred to as psi prime. So, this you can see is an integral in Dirac notation. I am sure you have done this in quantum mechanics, right? The Dirac Brown-Ket notations, right? M is referred to as the transition moment. It is also referred to as an integral because this is an integral, essentially what you are solving. Finally, you get a certain value which is the transition moment. Okay. So, this, guys, let me tell you, if you are doing electronic spectroscopy, this is something you will always have to deal with, and this is finally what defines your absorption spectrum, your fluorescence spectrum, whatever you see, it comes from here, because it is an overlap of two wave functions. If you are doing an absorption, it is an overlap between, see, if you are going to have an absorption, then it is an overlap between your ground state and the excited state. If you are going to have an emission, what will happen? It is an overlap between your excited state and the ground state. But it does not matter, whenever you are having any transition, what is going to happen is your electrons are going to move faster and the nuclei are going to follow it. Okay? That is essentially always what happens. So, now this being the most important thing, so this would be equation number 4, we need to solve it. Okay? But you will see the solution is not that bad, okay, to get to the final expression. That is what I mean. What we do now is, because we know that psi prime and psi double prime can both be split into what? The electronic and the nuclear components, or the electronic and the vibrational counterparts, right? Then we expand this integral. So, what we say is now, therefore, m based on our discussion is equal to, I will tell you why I am giving a double integral, is equal to this. What do you have? The psi prime can be written as psi e prime, and because this is on this side, it comes with a star, psi v prime star. It is like psi star h psi. Do you remember that? When you would do an expectation value, psi star h psi. Essentially, that is what I am doing. I am doing psi prime star, then the operator, then psi double prime. Your operator was mu, so I write mu out here, times psi e psi v, this is double prime being the ground state. Okay. Then what you have is, you will be having your volume elements, but how many volume elements would you be having here? How many volume elements will you be having? What are the coordinates involved? Good, you will be having 6 volume elements, that is true. So, essentially I can say, without splitting each volume element into 3, but volume element will be having 2 though, individual will be having 6, right. So, volume elements, there will be 2 volume elements. One volume element will be defined by the coordinates of the electron, the other volume element will be defined by the coordinates of the nucleus. So, I would be having d tau e, then d tau n. So, this would be equation number 5. Okay. With the thing, remember that psi electronic depends upon small r and big R, psi vibrational depends only on big R, right. So, then we go to the next step. What we now do is we split this by doing psi e star psi v star, then mu can be written as what now? Mu has 2 components, right. One is mu electronic, the other one is mu nuclear. Did I write mu n or mu v? Okay, I write mu n, good. Then psi e psi v d tau e d tau n. Okay. So, hence you will be solving essentially 2 integrals, okay. One which would be having only the mu electronic as the operator, the other one would be having the mu nuclear as the operator. Okay. Let us do that quick. So, this can be split into two. So, I can write psi electronic star psi v prime star, then I can write mu e psi e double prime psi v double prime d tau e d tau n plus, now I will bring in the mu nuclear psi v prime star mu nuclear psi e psi v double prime d tau e d tau n. So, that means your transition moment is now a sum of two very generalized integrals, okay. One which has mu e and the other one which has mu n. Okay. Now, if it is mu e, which wave functions are going to be affected? See, it is the electronic dipole moment. So, which wave functions would be going to be affected? Psi electronic, good. If it is mu n, which wave functions are going to be affected? Psi vibration, which is psi n essentially, right. Okay. So, you have to keep that in mind. Now, let us look at the second integral. Okay. Let us take a look at the, so let this be equation number 6 at the second term of equation 6. Let us look at the second term of equation 6. Let us see what we have. Okay. So, the second term can be written like this, sorry, psi v prime star psi v prime star, okay, let me write it again, missed one, psi v prime star, then I have mu n, then psi v double prime, okay. I have another integral, I should not be forgetting that integral, which is psi e prime star psi e double prime. Let me put this in large brackets. Here I will be having d tau e, then I will be having d tau n. Okay. Is it okay with you how I have written it? What I have done is I have just separated out the nuclear component from the electronic component, keeping in mind that mu n will only be sandwiched between which ones? The psi n's, which is essentially the psi v's. You will be having an integral which will be having psi e prime star psi e double prime with d tau e, because that is the integral with electronic coordinates, and because your integral electronic integral also depends upon the nuclear coordinates, that is why I have d tau n at the very last, okay, because d tau n is like a father figure for everyone, you know, everything depends upon d tau n. Okay. Now, guys, tell me what is the value of this integral? The answer is very simple, 1. Okay. What is the other binary digit? 0. Very good. So, at least he pointed us to the answer, right. Okay, it is not 1, it is 0. Why? Tell me why you said 1. You can tell me why it is 0. Which one is orthogonal, right? Which one is orthogonal? The second integral is orthogonal. The second integral satisfies the orthogonality. Do you understand that? So, look at this one. So, if you look at this one, which is psi e prime star psi e double prime d tau e, wouldn't this be equal to 0? Wouldn't this be equal to 0? For example, let us say this, you are taking a particle in a box, let us simplest example, particle in a box, right. How many wave functions do you have? Say you start from n is equal to 1, you cannot go to n is equal to 0 particle in a box, so you have psi 1, you have psi 2, you have psi 3 and so on. If you take an integral between psi 1 and psi 2, what would it give you? Psi 1 and psi 2 would always go to 0 because of orthogonality, right, because they are what, they are energy functions of the same operator, which is the Hamiltonian. Okay. Here too the psi electronic double prime and psi electronic prime, they are wave functions of what? The Hamiltonian, the electronic Hamiltonian of whatever system you are considering, hence they would be orthogonal. So, therefore, this is equal to 0 based on orthogonality. Okay. This would be equal to 0 based on orthogonality. Is this clear to you why it is orthogonal? Because if you would be solving hydrogen, say you are solving a simplest one, say you are solving say hydrogen atom, okay, you will be having this different quantum numbers n 1 2 3 4, right, but if you would take psi n equal to 1, psi n equal to 2, right, if you do an integral, what will you get? You will get 0, but then where do they come from? They come from solution of a single Schrodinger equation where H is always defined for you. So, they belong, that is what an orthonormal set is, right. An orthonormal set is formed from that set of wave functions which is coming from the same operator, and here these two belong to the same operator which is a H electronic, that is why they are orthogonal to each other. Okay. Good. So, that means the equation or the expression is already simplified for us. So, what does equation 6 reduce to now? Therefore, equation 6 reduces to m equal to, I can write psi electronic star psi v star mu e psi electronic double prime psi v double prime d tau e and d tau n. Let this be 7. So, this is the one I would be focusing on now, because the other one is of no consequence to us, right. Okay. Now, here too guys, here too I can split it into kind of, I can bunch it into two groups. What are the groups? So, this would be equal to, I can write, so I can write psi e prime, okay. Then I can write mu e, this is star psi e double prime, okay, like this. I always forget the volume element which is d tau e, then psi v star psi v double prime d tau n. Okay. I have already clumped it into 2. I have already clumped it into 2, right. Okay. So, this represents what? This represents what? This represents an electronic transition. This represents an electronic transition between two states, psi e double prime which is the ground state, psi e single prime which is the excited state, right. I should not be writing psi e double prime, well, psi e double prime is essentially means the ground state, but just keep that in mind, okay. Double prime means the ground state, okay. Then mu e. So, you take your dipole moment operator mu electronic, you operate it on the ground state psi e double prime. Where do you end up in? Where do you end up? You end up in psi e single prime. So, this is your electronic transition. This is your electronic transition, okay. This is your electronic transition. Now, what am I left with? I am left with two vibrational wave functions. One vibrational wave function belongs to the electronic ground state, the other vibrational wave function belongs to the electronic excited state. Now, tell me, this is an overlap actually, but tell me, would this be 0 or not? Hey, if this is 0, you know the answer is not 0, right, because everything goes to 0, there will be no transition, no spectroscopy, we will not be talking about this, right. So, you can safely now say that the answer is 1. Hold on, not so quick, then the answer is not 0, right, the answer is not 0. Now, tell me, why is it not 0? Why was the previous one 0? Why is this not 0?
There is a cross overlapping terms.
There is a
Overlapping terms between the excited state and ground state.
Well, I mean, this is an overlap term you are looking at. This is an overlap integral you are looking at. Why is it not 0? The other one was also an overlapping in that sense. Why is this not 0? Why was the previous one 0? What is the difference? Operator, right? Operator, you are in the right direction. Is the operator same or not? Hey, listen, when you are doing the electronic, when you are solving for the electronic, you are solving with only one Hamiltonian, right? When you go to vibration, what happens? When you go to vibration, you not only have your kinetic part, you also have your potential energy part, half kx squared, right? Now think about this, when you are doing a transition, in most of the cases, what would happen is, you would give rise to a change in bond order possibly. In most of the cases, bond order, or even you are shifting in distance, that means there would be a shift in the equilibrium geometry. Well, it does not matter. The point is, if your bond order is changing, that means the force constant is changing. What is the potential for a harmonic oscillator? Half kx squared, okay, but that kx squared, k is defined for each and every electronic state. So that means, if you have the ground electronic state, your k would be k ground. If you have an excited electronic state, your k would be k excited, and in most of the cases, this k excited would not be the same as k ground. Otherwise, you would not be observing any change at all. So that means, when you are solving for these two vibration levels, your Hamiltonian has already changed. And please remember now, they do not form an orthonormal set anymore, because the Hamiltonian has changed. Is this clear or not? It is not clear, okay. So let me write this and I will explain. So going forward, then m can be written as this, okay, can be generalized as this. I can write it as psi e mu electronic. So this is E means electronic, psi e right, okay, double prime. Then I can write psi v prime, sorry, I am just making a mess of it, anyway, sorry. So do not write this star here, please remove the star, read it again, psi v double prime. So this essentially is psi e prime mu e psi e double prime psi v prime psi v double prime, okay. So this is what your m is, this is your electronic transition, as I wrote last time. This is referred to as vibrational overlap, okay. This is referred to as vibrational overlap, right, it is overlap between two vibrational wave functions, okay. So coming back to our discussion, psi v prime and psi v double prime are belonging to two different electronic states, first keep that in mind, okay. Now if that is so, think about this. We were briefly discussing this last class. If you take ethene, right, or ethylene, what you would do is you would do an excitation, that means your HOMO, which is highest occupied molecular orbital, is filled with 2 pi electrons, right. You do make a transition from HOMO to LUMO. What happens is you have one electron in the anti-bonding orbital, essentially, if you go by molecular orbital theory. Initially your bond order was what? 2. Now when you go to the excited state, what is your bond order? 1, right. Because the bond order is 1, you know, if you would ever want to do a cis trans isomerization on substituted ethylenes, you do an excitation, and because then the bond order is 1, it will just move around the bond, and then when it relaxes, you might get an equilibrium between cis and trans, okay, depending upon what you start with, right. Now that is way of doing an isomerization, but anyway, the idea was this: your Hamiltonian for a harmonic oscillator is what? It has a kinetic energy term and it has a potential energy term. So for a harmonic oscillator, for Hamiltonian of a harmonic oscillator, HO, a harmonic oscillator, would be given by a kinetic energy term and a potential energy term. Now, if you are considering a linear, that means a harmonic oscillator in one dimension, say x, what is V equal to? Half kx square, where x is the amount of change you do from the equilibrium position, right. Okay, now tell me this, if I am doing an ethylene, right, if I am doing an ethylene transition, one electron goes to the anti bonding, in the ground state V ground would be half k ground x squared, right. Okay. Let this be x g, V excited would be half k excited x e squared. Now, this you should be able to recognize, because this is of fundamental importance. The moment you make a change from a double bond to a single bond, isn't your force constant changing? It has to change, right, because you look at a IR frequency, C double bond C, single bond C, all these frequencies come at different places. One bond is stronger than the other bond. So, that means if you are making a change from a double bond to a single bond, wouldn't k change too? Now, the moment k changes, because your k is intrinsically involved in the Hamiltonian, isn't your Hamiltonian changing too? Do you understand that or not? Because your potential is not changing, because you moved from one potential energy to a well to another potential energy well. Now, because the Hamiltonian has changed, no longer are they orthogonal, because they do not belong to the same Hamiltonian. That was how you define an orthonormal set, if you go back to your postulates. Okay. So, that is why psi v times psi v prime times psi v double prime in general is never 0. Only in certain cases, now you can tell me when can it be 0? It can be 0 only when the potential energy in the upper excited state looks very similar to the potential energy in the ground state. Only in that case would there be no vibrational overlap, essentially, that is what you are saying. That means this one would be almost gone. Okay. So, then what we can write down is, based on this discussion, so that means these are different. So, based on this, what we can write down now is psi v prime psi v double prime is not equal to 0 in general. So, this guy again was referred to as the overlap integral. It is called the Franck Condon overlap. It is referred to as the Franck Condon overlap. It is referred to as a Franck Condon overlap, and the intensity of a transition, whatever intensity of a transition you see, is essentially proportional to the square of this, is essentially proportional to the square of this. So, for example, the intensity is proportional to psi v prime psi v double prime squared, and this square is called Franck Condon factor. This is called Franck Condon factor. So, Franck Condon factor is just the square of your Franck Condon integral or overlap integral, right. That is essentially what it means. So, what you just saw is that if you would ever want to know on what the intensity of a transition would depend, it would depend upon this, the square of this Franck Condon overlap. So, instead of dealing with the square, it is easier for us to just deal with the overlap. Okay. We just then we will square it later, right. Okay. So, again, having said this, what would the equation number be for this one? So, what was the last equation? Okay, m, I did not keep an equation here. So, if for 7, this one would be 8, is it? If this one is 8, then I can say this one is 9. Okay. Now, guys, coming back to what we had derived before, this m has two parts. One is the electronic transition and the other one is a vibration overlap. Now, do you realize why it is called a vibronic transition? it is called a vibronic transition because when you derive the expression for m, it is just not either vibration or not only electronic, it is what? It has the electronic transition moment integral times what? The vibration overlap, and these two give rise to a transition which is referred to as a vibronic transition. That means, whenever you are doing an electronic transition, you will also have possible vibration overlap, and that is vibration transitions would be occurring too. Is it clear? What do you mean by vibration vibronic transition? So, you would see, so that is why you would see vibronic vibrations give rise to mixing of states. So, you would see that there are many transitions which are not allowed, but because of mixing they actually get allowed. You guys have all read a lot of these spectroscopic these things like Laporte forbidden and all these things, right? Okay, this is essentially come from here. Even if some transition is forbidden, you would see there is a little evidence of the transition occurring still, and because of these mixing of wave functions, that is where it comes from. But anyway, so that is not a point of discussion right now. So, again this m is the transition moment integral. This is what defines the probability of a transition. The probability is essentially the number of molecules which would end up there in the excited state, and then the number of molecules would easily transform to what? The intensity of the intensity of a transition essentially, and hence intensity is proportional to your Franck Condon overlap squared. Okay. So, now coming back to see some of these effects on these slides. So, let us look at this. So, this was a Franck Condon transition. Okay. So, this was a Franck Condon transition. As I said, I would always go with a vertical transition. So, this is a vertical, and I would never go for this. Okay. I can never have a change in nuclear coordinate. Now, what you can see here is, see, this is very important. You look at the blue one, right? You look at the blue one. In the ground electronic state, you have vibration levels. So, V0, V1, V2. In the excited electronic state, you also have vibration levels. You have to have, right? Okay. Now, if you are talking about the ground electronic state, which vibration level would be most populated? It would be V0. Okay. So, based on room temperature, based on thermal energy, based on Boltzmann population, most of the molecules, the major share of the molecules would be in V0. That means, whatever transition you are looking at from the ground state would essentially happen from where? Would essentially happen from V is equal to 0. Okay. Good. Now, if you look at the wave function, where does it max? The wave function maxes in the middle, right. So, then if it is the middle of the well, I mean this is your well, if it is the middle of the well, then the transition, the maximum probability of the transition would be occurring from the middle. So, that is why you see this is occurring from the middle. Okay. Now, because the transition is vertical, this would not care what has happened in the excited state, it will just go up vertically straight. Okay. Tick, fine. So, now it goes up vertically straight. Now, what you see is, when you go and look at the excited electronic state, is the excited electronic state same or different from that of the ground state? In what way is it different? Tell me. There is a difference. In what way is it different? Tell me the most obvious way it is different. What has happened? The nuclear coordinate has changed. That means, if this is your R equilibrium for the ground state, that means for the ground state, the R equilibrium for the excited state hasn't it changed? So, this is R equilibrium for the excited state. Hasn't that changed? That means, what has happened? That means, the average distance or the equivalent distance between the two nuclei has increased in the excited state. Now, that is what we were talking about in case of ethylene, right. If you would make it from a double bond to a single bond, obviously its length would increase. That means, the distance between the nucleus, the two nuclei would increase, the two atoms. Okay. Right. Now, the moment you have it shifted, what has happened is, the R equilibrium of the excited state is no longer on top of the R equilibrium of the ground state, because if this is the R equilibrium of the ground state, based on this it has already shifted here. Now, because it has shifted here, you see when you do a vertical transition, where is the maximum overlap of this transition occurring? That means, in the ground state it is V is equal to 0. With which state is it overlapping maximum? The third one, which is V2, right. So, that means, you can see the vibration overlap, which is the maximum, which is going to give you the maximum intensity, which is going to give you the maximum intensity, is the transition from 0 to 2, where 0 is the V0 of the ground state, electronic state, and 2 is the vibration level with quantum number 2 of the excited electronic state. Okay? Now, keep this in mind, we are talking about the vibrational overlap. This is what your Franck Condon overlap is, because the overlap is essentially what? Psi V prime, psi V double prime, that is what you are looking at. Okay? Right. So, 0 to 2 would be giving you the maximum intensity in your transition. Okay. Now, tell me, would this be the only transition that is happening? First of all, remember, all the transitions have to start from V is equal to 0 level, you have no other choice. Even if you have smaller transitions up there, they would be very much masked. Okay. You have heard of something in vibration spectroscopy known as hot bands, right? So, hot bands, you know how hot bands come from. So, that means if higher excited states are populated, right. But anyway, without going there, tell me, what are the other, or would there be other transitions possible in between the vibration levels? If they would be possible, why would they be possible? Tell me. See, this is not the only transition, try to keep that in mind, telling you the answer, this is not the only transition. If you look at a wave function is just not peaking at one point, it is peaking at one point, but a wave function is it's like this, it's encompassing the whole place like this, right. So, this is a wave function. So, this is how your wave function goes along with the tunneling parameters and all these things, right. So, that means if I am having electron density here, if I am going to do the probability density, then I will also be having electron density here. That means I can also make a transition from here, right. How do I draw? Okay. I can also make a transition from here. I can also make a transition from here. So on, right. So, you will see in the later slides what happens is you do not just get 0 to 2, because of this band, you will be getting multiple transitions, right. It is just not one transition. Now, what are these transitions? Okay, let us just avoid this right now. I will go to the transition and let you look at it. Here, this is what I was talking about. So, look at this. On the left panel, you have a nuclear configuration. In this nuclear configuration, you have a 0 to 1 transition. The 0 to 1 transition is your highest. The 0 to 1 transition means from V is equal to 0 in the ground state to V is equal to 1 in the excited state, right. Now, this is your absorption intensity, that means the intensity of a transition, okay, the intensity of a transition. Now, look at this, 0 to 1 you can see has the maximum intensity, because that is the most probable transition that is happening. What is it defined by? It is defined by the overlap of a vibrational wave function, the Franck Condon overlap. The higher is the value, the higher is the intensity. Okay. Now, because of this band, it is not so because of this band, the other transitions like 0 to 4, 0 to 3, 0 to 2 would also be there. That means, it is 0 from 0 to V is equal to 3, from V is equal to 0 to V is equal to 4, and so on. But because here the vibration is not as high, the extent of rather vibration overlap is not as high as that for which one, 0 to 1, hence their intensities would be lower. Okay. Now, the 0 to 0 transition, you can see this is a 0 to 0 transition, you can see this 0 to 0 transition. What does a 0 to 0 transition mean to you? A 0 to 0 transition means you are going from V is equal to 0 in the ground state to V is equal to 0 in the excited state. Now, this 0 to 0 transition is referred to as a purely electronic transition. The 0 to 0 transition or 0 to 0 transition is referred to as a purely electronic transition. Do you know why? Why? Because in the electronic ground state, your molecules are populated in the V is equal to 0. In the vibrational state, rather in the excited state, the molecules are also there in the 0 level. So, if you are doing a 0 to 0, the molecules have to be in the 0 vibration level, right, there is no other way, they have to be in the 0 vibration level. That means, you are making from 0 to 0, no other vibration level in the excited state is involved in that transition corresponding to that wavelength or that frequency, and is referred to as a purely electronic transition. Okay. Now, similarly, look at this. Next look at the right panel. See, in the right panel what has happened is the R equilibrium has shifted a lot. Because the R equilibrium has shifted a lot, as opposed to the previous case where 0 to 1 was the maximum transition, in this case it is no longer 0 to 1. What is the maximum intensity? It is not 0 to 4. It is 0 to 4 again simply because the wave function of your fourth vibrational state in the excited state has the maximum overlap with the wave function of your V is equal to 0 in the ground state, and that is why it has the maximum intensity out there. Okay, again as simple as that. But again, because if you have a band, and hence you would be looking at an envelope of transitions. So, this guys, whatever this you are looking at, these two, this is referred to as a Franck Condon envelope. This is referred to as a Franck Condon envelope. Franck Condon means just a vertical transition. Why is it envelope? Envelope means it is just not one transition, it is encompassing or it is enveloping under the shed a series of transitions 0 to 1, 0 to 2, 0 to 3, 0 to 4, and which one will be having the maximum intensity would be defined by the overlap integral, essentially that is how it goes, right. So, this is also referred to as a a vibronic overlap, or rather vibronic envelope rather, or Franck Condon envelope, and this is often seen if you would take absorption spectra, especially of organic molecules. If you take absorption spectra, you would often see bands coming up like this, which are referred to as your vibronic bands, and your vibronic bands just tell you that I have or you have excitations to higher vibration levels in the excited state, starting from the ground state vibration level of your ground state of a ground electronic state. Okay. So, just to wrap this up, so I have talked about the vertical transition. So, again the Franck Condon principle states that since the time required for an electronic transition is very small compared to that of nuclear motion, the most probable vibronic transition is the one which involves no change in nuclear coordinates, that we know. Next, this transition, often referred to as the Franck Condon maximum, represents a vertical transition on your potential energy diagram. This we have seen. Okay. Now, what does this say? Look at the left panel, it says no vibronic coupling. Why does it say no vibronic coupling? Now, look at this. What has happened is your R is equal to 0, rather your R equilibrium in the ground state and your R equilibrium in the excited state are very similar. Can you see? So, this one and this one, they are almost at the same R. That means your equilibrium distance is not shifted between the nuclei. Because it has not shifted, guys, because it has not shifted, so V is equal to 0 level would be right on top of V is equal to 0 level. So, V is equal to 0 in the grounds, in the excited state would be right on top of V is equal to 0 ground. So, which one would be having the maximum overlap anyway? The 0 to 0 transition, and because it is 0 to 0 transition, if you talk, as I said, if you are talking about any electronic state, your molecules would not be having a choice but to stay in this V is equal to 0 state. So, that means this is not involving any higher vibration levels, and hence it is called a pure electronic transition, no vibration levels involved. That is what 0 to 0 is. Okay. So, now you can understand how do you get vibrational bands, how do you get vibronic bands. So, if you go to the next one, what has happened is now it is no longer, the R equivalent is no longer the same in the ground and the excited state, shifted, and the moment you shift, the transition remaining a vertical transition, it will still go up, but it will overlap with another V in the excited state. So, say in this case it is V is equal to 1, and because you are having a change in a vibrational quantum number, say from 0 to 1, these being of two different electronic states, here you are having vibronic coupling. Okay. That means this is a vibronic transition, where you not only having an electronic transition means that you are going from S0 to S1 or ground electronic state to excited electronic state, that itself is an electronic transition. Not only that, but also when you are moving to the electronically excited state, you are occupying higher vibration levels of the electronic state, right, and that is why it is called a vibronic transition. Okay. So, we will stop here. So, this is essentially what your absorption spectroscopy is all about in terms of the theory. if you are talking about fluorescence, which we will do in the next class, fluorescence is just the reverse of this. So, you would see if you are getting an absorption overlap for the your overlap in the absorption, you are going to get a similar overlap in the fluorescence, because those are the ones which are going to come down vertically too, right, giving rise to something known as mirror image symmetry. So, and after that we will move on to Lambert-Beer's law, look at some issues in observance and try to move into fluorescence. Okay. So, that is it for today.